Hello everyone, and welcome back to our series on quantum mechanics. In the last video, we looked at the bound and scattering states of the finite square well. In this video, we will wrap up our discussion of 1D potential wells by looking at a special potential well, the quantum bouncing ball, or gravitational well. Suppose I have a hard surface at z equals 0, and I drop an object at a certain height z above it. Classically, we would say that the potential energy for the particle is simply the gravitational potential energy, which we describe via the linear potential V equals mgz. Now, suppose that our object is a particle on a quantum scale, such as a neutron. How does the wave function of such a particle change under this linear potential? This is the question we seek to answer today. In particular, we will assume that our surface is a perfect barrier, meaning that for z less than 0, we have that v of z is equal to plus infinity, and for z greater than or equal to 0, we have that v of z is equal to mgz. Plotting this potential, you can see that this potential goes off to plus infinity as z goes to plus or minus infinity, meaning that we have no scattering states. Furthermore, since the minimum value of the potential is v of z equals 0, bound states can only occur for e greater than 0. Okay, so how do we actually find the bound states? Well, in this situation, we'll have to actually solve this differential equation. However, there's a problem here. As it turns out, it actually isn't possible to solve this differential equation in terms of elementary functions. We could use a power series solution, but that would be pretty cumbersome. So what do we actually do here? Well, looking at the form of this differential equation, we can see that we have a second derivative term and this linear expression in z times psi. This looks pretty similar to this special differential equation, known as the Airy equation, which has known solutions given by special Airy functions ai of x and bi of x. Hence, if we can rewrite this ODE as an Airy equation, we can find psi in terms of the ai and bi functions. So, how do we reparameterize our equation as an Airy equation? Well, observe that the main difference between our equation and the Airy equation is the fact that the linear z expression multiplied by psi has an additional constant term. This seems to imply that if we perform some kind of parameterization that is linear at z, we can rewrite this equation as an Airy equation. In particular, we can substitute z equals aw plus b and rewrite our differential equation in terms of w. Note that we can use the chain rule to figure out what the derivatives with respect to w translate to in terms of derivatives with respect to z and vice versa. I will also use phi of w to denote the function psi of aw plus b. In order for this differential equation to become an Airy equation, we require the coefficient of w phi to be 1, and the constant multiplied by phi to be 0. This gives us the following set of equations, which we can then use to solve for a and b as follows. Consequently, since we now have an Airy equation, we can use the formula for the general solution, which is simply written as follows. Rewriting this in terms of psi and z gives us the following. Okay, so we have an ansatz for a solution, but what are these coefficients c1 and c2? After all, the normalization condition alone is not enough to define both of these constants. Well, to answer this question, let's plot both the ai and bi functions. We can see that for negative x, both functions have oscillatory behavior, similar to sine and cosine, while for positive x, ai of x decays exponentially, while bi of x increases exponentially. In essence, these functions capture both oscillatory and exponential-like behavior. Asymptotically, these functions actually behave like either sine, cosine, or exponentials of plus or minus 2/3 times x to the 3/2 power, with some additional offset or scaling. This combination of oscillatory and exponential-like behavior makes sense if you look at the differential equation, since the sign of x controls whether the differential equation is similar to that with sine solutions versus exponential solutions. Looking at the asymptotic behavior of both functions, we can see that bi goes to infinity as x goes to plus infinity, meaning that a bound state with a non-zero bi term would be unnormalizable. Consequently, we must have that c2 equals 0. Now, of course, c1 is simply just a normalization constant. Nevertheless, there's a problem here. I've defined the bound state in terms of the energy E, but I've never actually stated what the allowed energies are. Well, the selection rules for the energy are simply determined by the one boundary condition we actually have, which is that psi of 0 equals 0. Denoting a sub n for n equals 1, 2, etc. as the nth zero of the Airy function, we can compute the allowed energies as follows. Consequently, we have the following eigenstates and their corresponding energy levels. Plotting the first few eigenstates at the height of their corresponding energy levels overlaid on the potential, you can see that we get the following behavior. Essentially, the bound state is oscillatory between z equals 0 and the classical turning point, and then transitions to an exponential type of decay. As I stated before, this decay is actually faster than exponential. This should make sense since for a constant potential, like in the finite square well, the decay was exactly exponential, and for the quadratic potential, the decay was Gaussian. Since the wave function should decay faster when potentials rise quicker, we have that the decay for a linear potential should be something between that of an exponential e to the minus x and a Gaussian e to the minus x squared over 2, which is exactly what we have, since the decay goes asymptotically as e to the minus 2/3 x to the 3/2. Altogether, we explored the gravitational potential well as a way of illustrating how we can use traditional differential equations techniques to solve for eigenstates, and what to do when we can't express solutions in terms of elementary functions like exponentials, trigonometric functions, or logarithms. This concludes our chapter on 1D potential wells. In the next video, we will take a big leap and jump straight into quantum mechanics in 3D, so stay tuned for that. I hope you enjoyed this video, and I will see you next time.